As today we've got a triple integral in cylindrical coordinates. We're going to knock this one out. We're going to see how to get the bounds in cylindrical coordinates for some really cool shapes, or this shape here actually. All right, so look at this integral. Evaluate by switching to cylindrical coordinates. We have the triple integral over some solid region Q, 1 over the square root of x squared plus y squared dv, where Q is the region outside the cylinder, x squared plus y squared equals 1, under the paraboloid z equals 9 minus x squared minus y squared, and above the xy plane. All right, so this is going to be a triple integral. We switch to cylindrical coordinates. We got to figure out the bounds for this solid region Q. So the solid region Q sounds kind of complicated, but once we dissect it a little bit, we'll be able to figure out what the solid region is and how to get the bounds for our cylindrical coordinates. So we'll look at integrating z first. So there's going to be two ways that we could do this. We could integrate z first, or we could integrate r first. What we're going to do is we're going to say z is going to go from the xy plane up to the function or the surface. So z is going to be bounded by the surfaces, and then r is going to be bounded by numbers. So this paraboloid was z equals 9 minus x squared minus y squared. If we look at the traces of that, the traces in the x equals a constant, so in the yz direction, the traces are going to be parabolas that are opening down. And same thing in the x direction. If I let y be constants, then in the xz direction I see parabolas that are opening down. So regardless, I see parabolas opening down. And then if I hit the xy plane down here, so when this thing hits the xy plane, looks like it's going to create a circle. So in the xy plane, that's when z equals 0. If I set z equal to 0, then I get 0 equals 9 minus x squared minus y squared, which is really just a circle of radius 3. So x squared plus y squared equals 9. The trace z equals 0 of this paraboloid is just a circle of radius 3. So this circle of radius 3 is this z equals 0 trace. So that tells me some information at least about the paraboloid. The cylinder looks like this. It's an infinite cylinder in the z direction. So it would actually be going through the paraboloid at some point. So the cylinder is going to go through the paraboloid at some point. But the radius is 1, so actually it would be inside the paraboloid. And then eventually it would burst through the paraboloid. So we want to stay outside the cylinder, but inside the paraboloid and above the xy plane. So that's going to be our region of integration. So I've got a better visual than this, sketchy drawing that I have here. All right, so if we look at the solid region here, we see the paraboloid and the cylinder actually intersect. So the cylinder is inside the paraboloid, and I've left off the z equals 0 plane, or the xy plane, so we can see underneath. And if we zoom in, we see that our region of integration is the part inside the paraboloid, but outside the cylinder. So we want to stay outside the cylinder, but inside the paraboloid. All right, so that means our radius is going to go from this cylinder out to this radius, while z is going from z equals 0 up to the paraboloid. So the bounds for z are going to be 0 to the paraboloid, and the bounds for r are going to be the cylinder radius to the radius of this circle down here in the xy plane. So actually that would be, if we look at this trace in the xy plane, it's actually just a radius of 3 right there. So radius of 1 out to radius of 3 for r, and then 0 to 9 minus, in this case, r squared if we switch it to cylindrical coordinates. All right, so describing this with bounds that are going to be integrating z first are going to be, z is going to go from 0 to the paraboloid, 9 minus r squared. If we convert the paraboloid into cylindrical coordinates, that'd be 9 minus r squared. So that's the bound for z. Z is going from 0 up to the paraboloid. And each part of this disk, we're going from 0 up to the paraboloid. Right? And then r For what values is z going up to the paraboloid? Well, for all r values between 1 and 3. So for all r values between 1 and 3, our upper bound for z is the paraboloid and the lower bound is 0. Theta is usually an easy target as far as figuring out the bounds. That's going to be 0 to 2 pi. So theta goes from 0 to 2 pi. So this is going to be the integral 0 to 2 pi, integral 1 to 3, integral 0 to 9 minus r squared. And then our function was 1 over the square root of x squared plus y squared. So changing that integrand, this integrand is going to become 1 over r, because this is the square root of r squared. X squared plus y squared equals r squared in cylindrical coordinates. So then taking the square root of r squared is going to be 1 over r. All right, so that's going to be our integrand. So integrand is 1 over r. And then our dv in cylindrical coordinates is always r dz dr d theta. Of course, that's assuming we're integrating z first, and here we are integrating z first because we set up the bounds that way. So these r's are going to cancel. That's nice. So cancel the r, the 1 over r. Actually, it's going to be pretty easy to integrate. Get the integral 0 to 2 pi, integral 1 to 3. Integrating dz, 1 dz is just going to give me z from 0 to 9 minus r squared dr d theta. And actually that theta term, I can just pull that over, the d theta, directly over here and get 2 pi from that integral. So I get theta, which goes from 0 to 2 pi directly from doing d theta. And then I'll integrate from 1 to 3, 9 minus r squared dr, which is going to be 2 pi times, that'll be 9r minus r cubed over 3 from 1 to 3. And that will be 2 pi times 9 times 3 minus 1 minus 27 minus 1 over 3. And that reduces down to 56 pi over 3. 56 pi over 3. And that is the value of the integral. Okay, so if we look back at this region, there's another way to describe this in terms of bounds. Like if we wanted to integrate r first, we could say r as a variable is going from the cylinder out to the paraboloid. So from 1 to solving the paraboloid for r, it would turn out to be square root of 9 minus z. We'll see that when we do it. And then z goes from 0 to wherever the paraboloid and the cylinder intersect. So z would be between constants if we integrated r first. So let's set up the integral with r being integrated first. So if r is being integrated first, our paraboloid was z equals 9 minus r squared, then r squared would be equal to 9 minus z, which would tell us that r would be square root of 9 minus z. So that would be our upper bound, or our outer bound, we could say, for r. So r would go from 1 to the paraboloid, square root of 9 minus z. Now z goes from 0 to wherever they intersect. So height of intersection. So where does the cylinder intersect the paraboloid? Well, that's when x squared plus y squared equals 1 intersects z equals 9 minus x squared minus y squared. Well, that would just be 9 minus 1. If we substitute this relationship x squared plus y squared into the paraboloid equation, we would just get 9 minus 1. So actually z would go from 0 to 8. So the height of intersection is 8. So the bounds of z are 0 to 8. Now, the bounds for theta are the same, 0 to 2 pi. So I've got my bounds for r, I got my bounds for z, I got my bounds for theta. Now we can do the integral. So this is going to be integral 0 to 2 pi, integral 0 to 8, integral 1 to square root 9 minus z. Then we have 1 over r dr dz d theta here. So we're doing r first. So integrating r first. Well, these r's still cancel. So this is going to be integral 0 to 2 pi, integral 0 to 8, and then r goes from 1 to square root 9 minus c dz d theta. Again, there's no theta in the bounds or in the integrand anywhere, so I can pull the d theta over here directly, integrate that, and get 2 pi. So this is going to be 2 pi, integral from 0 to 8, and then plug these bounds in. That's going to be square root of 9 minus z minus 1 dz. And to do this integral, we would need to do a u sub. So this is going to turn into 2 pi, integral from 9 to 1, square root of u minus 1 negative d. Now we're going to use this negative sign to flip the bounds. That's the property of a definite integral, is that we can flip the bounds by inserting a negative sign. And actually, since we already have a negative sign, it'll cancel. So we will flip the bounds and cancel that negative sign. So this is going to give us 2 pi times integral from 1 to 9, square root of u minus 1 du. This is going to be 2 pi, 2/3 u to the 3/2 minus u from 1 to 9. That's just going to be 2 pi times 2/3 times. See, 9 to the 3/2 is 27. 1 to the 3/2 is 1. Minus 9 minus 1. And this is going to reduce to 56 pi over 3. Same answer we got before, 56 pi over 3. So get the same answer, just integrating r first. So no difference in the answer. Of course, that's the way it should be. That's how we do it.